Dear colleagues and friends, welcome to the 17th session of our Socio-Economic Metabolism Perpetual Online Conference. This long title dates back to the pandemics, where we said we need an online exchange format to keep the global community connected together. So we have, over the last 4 years, had now in total 17 sessions with quite a few participants on various different topics, critical materials, stock and flow modeling. And today we talk about a new research arena. This is the modeling at the urban scale. So for today's session, I'm very pleased to have three speakers with us. There's Dr. Yupeng Liu from the Chinese Academy of Science at the Institute of the Urban Environment in Xiamen, China. We have Keagan Rankin, University of Toronto and University of Cambridge. And there's Lola Rousseau from NTNU Trondheim, Norway. The three of you have done cutting-edge work on modeling stocks and flows, material and energy at the city or regional scale, and you agreed to present your work today. So thank you a lot for that. And of course, we thank all of our participants who join us online today. We have I can say this, this series is independent of the IE day, but of course we are the same people. So many of us will also organize sessions on the Industrial Ecology Day 2 weeks from now. So we will make announcements later on what's going to happen here. So today we have the topics of city modeling as part of the SEM section online conference, and in 2 weeks with the Industrial Ecology Day, other sessions will continue on vehicles, on critical materials. A lot of stuff is happening. And now I'm happy to give the word over to you, Yupeng, for presenting the material saving strategies in the global building stock.
Yeah, thank you. So I can share my screen.
Yes, please.
Yeah. So could you watch this, my screen?
It's perfect.
Okay. Is there any block on the top of the screen? No? Oh, yes. Oh, that's it. Thank you. Okay. Hello, everyone. I'm Yupeng. It's my great pleasure to have this opportunity to show our work on scenario modeling of urban metabolism. I think, let me try. So, first of all, I want to briefly introduce myself. Okay. I'm Yupeng. My background is remote sensing and geographic information system. So then I use these tools during I was a PhD student. Yeah, actually, I conduct the studies in the field of urban ecology, like the topic on urban heat island or urban air pollution to get my PhD. Actually, since 2017, I became a faculty member in the Institute of Urban Environment, Chinese Academy of Sciences. And also I firstly involved into the field of industrial ecology. Actually, since 2027, I also served for the Urban Health and Wellbeing Program leading by the International Science Council. Uh, so my study right now focuses on quantifying material stock and flow in our cities and between urban dwellers and environment. What we want to do is trying to open the black box. We call that so-called the black box in urban metabolism through better understanding what are they, where they happen, and how they're processes to improve material and energy usage, efficiency, reduce their environmental footprint, and avoid negative impacts. So toward more sustainable cities and improve human health and well-being. Actually, right now, our study focuses on building material metabolism because the building is related to many important goals on sustainable development, including, for example, the urban form or urban morphology, transportation, waste generation and treatment, climate change, even human health and well-being. For better quantifying building material stock and flow, we actually our work starts from the data collection, then model development, and finally to do a global scenario assessment. So actually for the data part, my background is remote sensing and GIS. So we try to extract like building outline or footprint based on high resolution remote sensed images or data to get building so-called two-dimensional information. And then we also try to retrieve building height and layers or floors to get the three-dimensional information of these buildings. So with this data, we could characterize urban three-dimensional patterns and dynamics and try to recognize its morphology changes. And of course, based on this data set, we also could try to estimate some building attributes for including like vintage, structure, the brick concrete structure or steel concrete structure, and usage like residential, commercial, or non-residential buildings. So based on this information, we finally created a database to try to support the material stock and flow quantification. So based on this data set, we also here we try to develop, we call that building metabolism model, actually by combining material flow analysis, a typical tool in the field of industrial ecology, and of course some popular tools in the geography, like the Geographic Information System, the GIS. So actually this model, it's actually equals to, it sounds more like a stock-driven GIS-based material flow analysis. So with this model, we could try to estimate it material flow, stock, and flow for every, for example, 1 kilometers time 1 kilometer grid in our map. So first of all, we try to test this model for individual cities and try to simulate and monitor the three-dimensional expansion and related material stock and flow changes. So based on the good performance of the model, we use it for global assessment, try to answer more interesting problems. We try to scale it up this model from a city level to regional, even global scales, which could be answer more interesting questions. For example, we want to answer it's like what size of cities will expanded or are expected in the future, which of these cities or which part of these cities would rise or fall for future urbanization. And of course, a typical question in the field of industrial ecology, how many construction materials would be consumed for cities and future urbanization? And of course, what are the potentials for our cities to decrease material footprint by alerting future trajectories? So here I will briefly show what our results for global assessment. So it seems like globally, based on like the a data set, the global human settlement build-up volume data set published by the GRC, it seems like today we have more than 400 million square meters building around the world. And based on our estimation, for 2050, that number would be about 650. So that means a net 50% increase and expansion speed, which equals to building a brand new Shanghai or New York every month for the next 30 years. And of course, the building size for each country, it seems like China would still have the largest building stock, more than 100 up to 134 billion square meters by 2050. And of course, some developing countries like in Asia, like India, and some Africa countries like Nigeria would grow rapidly for their building stock. For example, India could triple its current building stock by 2050. And of course, for developed countries in Europe, like France, Germany, Italy, and some Asia countries like Japan, would possibly reduce their building stock compared to the values in 2020. The next, if we, that's the total size of building stock for each country. But if we use the per capita build-up infrastructure as an indicator to indicating for example, the equity of a country, it seems like the gap between the global south and global north would narrow in next 30 years. And of course, the second, if we keep zoom in to the city level, we will find different tendencies of global cities. Like Mumbai in India, it will grow more outward and upward. For LA, Los Angeles, it will grow vertically. And for Johannesburg in South Africa, it seems like the city will keep stable. And of course, an old city in Germany, the Berlin, could be shrinking at downtown area, but building will grow in the surrounding in the rural area, which leading to a flat city than ever. And of course, for Tokyo, for number five, typical cities like Tokyo in Japan, due to the decreasing in population, it seems like the total building stock in Tokyo and Japan seems would go shrinking. And of course, beyond those changes of buildings, a typical question is that how many construction materials will be consumed for cities and future urbanizations? Our preliminary estimation, it seems like the urbanization will ask for more than 300 gigatons up to 650 gigatons of construction materials for next 30 years urbanization, which equals to about one-fourth or up to 60% of the in-use man-made mass on the Earth now. And of course, the developing countries like Asia, in the Asia area and developing Pacific region will use the most, a total of more than 120 up to 270 gigatons of materials will take little less than half of the global need for next 30 years. And of course, the Asia and the Middle East region also is very will develop very fast, will ask for about 68 to 100 and 150 gigatons of construction material, take about one-fourth of global needs. And of course, our model also could try to estimate it, the purpose of this material used. Apparently, different countries use those materials for different purpose. For example, for developing countries like China or India, most of these materials would be used for future urbanization and expanding their building stock and their cities. But for developed countries like the US, will use more than two-thirds of these materials for building replacement or renovation. And similar patterns also could be found in, for example, Australia, France, Italy, Germany, and Japan. And in contrast, more than three-fourths of the construction materials in India and more than half of them in China will be used to fulfill the booming needs for brand new living and working spaces needment. So next question is that possible to decrease our future material footprint? So here we design many potential, we call that material saving wedges, because that the shape of this wedges can changing among different passes. For example, we design 5 typical material saving wedges. For example, from the source, from the beginning, we could try to reduce demand for future building stock. It seems like demand side mitigation to avoid oversized dwelling and superfluous spaces for sharing, for example, common spaces and related approaches. The second, which we call that lifespan extension, LE, extending the lifespan of in-use buildings can also mitigate future building demand and reduce the size of new construction and related material consumption. And third, which is material diet, means we use more emerging technologies serving material efficiency, such, for example, the three-dimensional printing, or use more environmental friendly materials like wood or straw instead of like carbon intensive materials like steel and cement. And of course, we usually emphasize the 3R, the reuse and the recycle, those demolished construction materials from demolished buildings can directly reduce raw material use. And of course, some new emerging construction technologies like prefabricated buildings, the PB, construction buildings with pre-ordered and factory-made components could avoid a little of this material loss and debris generation during the construction processes. Actually, based on our estimated, we test these material saving wedges one by one independently first, and then we try to combine them together to show the cumulative contributes of these wedges. So based on our estimation, it seems like for the largest or greatest contribution or effects, for example, the reduced demand uh, can reduce about 70% of the future materials. The life extension saving 16% of future material use, and material diet because we use that huge amounts of the wood to instead of those steel or cement. That means we can save lots of materials and embodied carbon emission by this, which is, and of course, 3R or double R reuse and recycle materials here can help us save 16%, and prefabricated buildings can help at least 1% of the future material saving and greenhouse gas emissions emission. So if we combine them, the cumulative effects is seems like more than half of future material use, or up to maybe 90% of future material use. I mean, more than half and up to 90% of materials and embodied carbon emissions could be saved for combining these five combining material saving wages. So, and of course, recently I congrats to Stefan, which published a good paper in the GIE. So let us have a good chance to compare and discuss related like store floor services nexus for future urbanization and building stock growing. So it seems like in Stefan's paper, the global building stock in 2060 would be 330 to 530 billion square meters in 2060. But for our result, it seems like our prediction is that 650 billion square meters in 2050. And I think the overestimation of ours mainly caused by the different start point. I mean, the in-use stock in 2020. It seems like the Stefan start from about 260 billion square meters in 2020, but ours is start from about 420 billion square meters in 2020. Uh, uh, However, I think that the net growth of global building stock for our two estimations are quite similar. Will net increase or net growth of future building stock will about 200 billion square meters increase for next 30 to 40 years. So this phenomenon leads to, I think, comparable estimation on material use and saving, which is about 10 to 35 gigatons of steel and about 30 to 100 gigatons of cement saving. But for the greenhouse gas emission saving, our study, I think that a more ambitious target, for example, we set 20 years prolonging for every global in-use buildings. That's quite ambitious. And of course, we try to set construction more wooden-based buildings instead of the steel and cement, and try to save more materials and embodied carbon emissions. And of course, we also set an ideally 100% of the reused demolished materials, which leading to, I think, higher greenhouse gas emission effects estimation for our study. So I think at last, I will show some take-home messages. So forgot about the absolute values for building stock differences between Stefan's work and our works. But for growing patterns and growing rates, I think the build-up infrastructure in next 30 years will grow faster in developing countries, which can very likely narrow the gap between the global north and south. And of course, it seems like the global man-made mass will have 30% of net growth due to the future urbanization and the business as usual scenario. But the good news is that more than 50%, more than half of the raw material consumption could be saved by combining those, we call that material saving wages, which helps to sustainable development goals achievement. And I think that's my presentation today. Thank you.
Yupeng, thank you so much. This was very compact, very exciting, very well organized. And of course, we will discuss everything together later, right? The findings and the comparison as well, also the modeling approaches. Now I would ask the audience if there's any immediate clarification questions. Please raise them now, else the larger discussion will happen in the end. Just have a quick look. And then let's now move on to our second speaker, to Keagan Rankin. From Keagan, you will have to tell yourself where you're based at the moment. I hope not in the middle of the night in Canada.
No, I'm in the UK right now.
Okay, that
Yeah.
helps. It's only your lunch break that we're eating into, literally, so to say. Keagan, you have also a presentation prepared, right?
Yep.
And
Let
then
me set it up here.
yes, exactly. So you recently published in Environmental Science and Technology a city level modeling using also machine learning to extrapolate, and you will report this today. I think this actually your paper was one of the motivations also to organize the sessions. I think more people should also know about this approach. So the floor is yours. At the moment, we can see the editing view.
Oh, okay. I will your presentation.
Maybe you
Is
can
that
talk
good?
there. Yeah, perfect.
Amazing.
All right. The floor is yours.
Okay. All right. Thank you, Stefan. And thank you, Yupeng. I thought that was a really interesting presentation, and it kind of leads well, starting at the global scale down to what I'm doing, which is a bit more detailed. So I'll introduce myself quickly. I'm Keagan Rankin. I'm a PhD student at the University of Toronto, working with Shoshana Sachs and Daniel Posen. I'm out kind of like on a research exchange this year. So right now I'm working with Andre Sorenho at the University of Cambridge. But this work was mainly done over the last couple of years with Shoshana at the University of Toronto. So I've kind of, like Stefan said, most of this is based on some work we just published in ES&T. I also wanted to start with a bit of background on the paper we did before that, because it leads very well into what we did. But the general topic of what I'm going to tell you today is about building more housing with less embodied greenhouse gases. So very similar to what we were talking about with buildings, but here I talk a bit more about infrastructure as well. I'll show you kind of the interesting modeling method we came up with, and then some of the results that we found, which were specific to Canada. So I'll start with the motivation behind this work. The thing that really motivated or kicked this off was in Canada, just like a lot of places in the world, we have this huge demand for housing because there's this huge deficit in the amount that we build for the last 50 years. And there's some great reports by some of the government research agencies in Canada that show we just needed this really crazy amount of housing over the next decade or until 2030 to achieve affordability. So it's not about development, because Canada has a developed economy. It was really about affordability of housing, and this is still a big issue. You see it in the news every day in Canada. So we were really interested in, as industrial ecologists, what would the impacts be if we built all this housing we need, obviously. We know that the embodied emissions, or the emissions that are associated with the materials that go into construction of housing, and also the infrastructure that supports it, like roads and water infrastructure, are they're significant, they're increasing over time, and there's not many good production ways to reduce them. So we wanted to see what would the impacts be, and how can we use demand side and material efficiency strategies to reduce those impacts. So I've kind of laid out three broad questions that we tried to answer with this research. The first one is, what's actually driving embodied GHG in housing and also related infrastructure in Canada? The second thing we wanted to know is, how do we reduce this? What's kind of the most effective way of reducing this embodied emissions, especially with this near-term large future construction that we want to do? And then third, can we actually answer that question we kind of set out with, which is, can we build all this housing that Canada needs? Could we reach that point where 10 years in the future, we have enough housing so that everyone can afford it, while still meeting some of the climate commitments that the government of Canada has set out? And I'll talk about those specifically in a bit. So starting off with this work, we were doing a bunch of data collection. So really, we were interested kind of in the beginning at building scale. What are the different choices in housing design and building design that reduce or increase embodied emissions? And we wanted to go really detailed. So this work actually started with Shoshana about 5 years ago, where she just started going to people and asking for building drawings, and then we would quantify them to a high degree of detail and kind of look and see what's the material mass in buildings, but also what is the embodied GHG associated with that, specifically in Canada. And can we kind of pinpoint hotspots and different things about housing design which might increase or reduce material use. So specifically, I was looking at housing form in this paper. So we started off saying, in Canada, for those of you who have never been there, or I'm sure many of you have been to North America, but compared to Europe, North America has a very distinctive housing style. So we have a lot of single family homes. So kind of these detached structures that one family lives in, and it's set out on a plot of land. And then we have these big downtown cores, if you think of like New York City or whatnot, where you have these large, high-rise, dense areas. But there's not this sort of in-between low-rise housing that you see in places like Europe and in the Netherlands, for example. So there's this term in planning that's become very popular in North America called missing middle. But anyway, we were trying to see, is there a difference between the material use of these different types of buildings and the efficiency of them? That's what we started with. And essentially the process was, we would go out, we'd find a building that looked interesting, we'd call up or email the person that owned it and said, hey, can you give us the building drawings for this? We would quantify those buildings in a building information modeling software like Revit, and we'd do this nice detailed model of basically every single column in the building, every slab, every door, and then what material they were, and then we coded that all into this nice database we have where we can easily query it. And we did this for about, I think now the data set's at like 200 plus buildings, but at this time it was about 100 residential buildings. And it doesn't sound like a lot, but like collecting this data took a long time. So it was, it's a very detailed data set, and to get 100 data points was a big deal once we did it. So with this data set, we can go and we can really, in a detailed manner, say, let's like isolate a specific building. Let's see all the different material types that are in it. Are they in the basement? Are they in the columns? What kind of materials are there, et cetera? And we did an analysis of this. So this is going back to the first point, what's driving the embodied GHG and the material use in housing in Canada. The paper lays out a bunch of stuff. I'll kind of hit the highlights here. The first thing we found is, even though we went into this looking at form, were single family homes better than high rise or the middle size, for example, what we actually found was, well, there was a difference in form, and the sort of middle size multi-unit homes tended to be the best in terms of material use. So they were the most efficient in terms of the material per capita, per bedroom. What we found was that there was this huge difference within form just based on kind of random or whatever arbitrary design choices that designers were making, architects, engineers, when they were putting up the buildings. So this is super interesting. You could have a single family home, which on average use quite a lot of materials per person. But if you, for example, made them a lot smaller and didn't use specific materials, you would have a much lower impact than maybe the average multi-unit building. So one of the big things we found, this is a big thing that we've talked to kind of everyone about, is that we saw this big underground effect across all the building forms. So in North America, we build with these big basements in small residential buildings, but also we have a large underground parking. And we found, because of the concrete impact of these, it had a huge amount of material mass for not a lot of useful space. So I'll give a specific example. In these high-rise buildings, you can see these two above ground are basically the exact same, but one of them has this big underground parking. And because of that, it has a much larger embodied GHG impact. So the kind of the outcomes of this was, hey, there's all these design changes that are really relevant within forms rather than kind of between them, and just looking at housing forms and telling the full story. And really what we should be doing is kind of looking at what are the best in class designs. Now this study was at the building scale, and then we wanted to go and say, how does this scale up? So this brings me on to the paper we started with, which is this infrastructure growth model we just published. And here, again, we were trying to answer that question, can we really go from the single building scale to the country scale and build enough within climate limits? Now, something I'll say here is that when we looked at a lot of previous models, a lot of them would use archetype input data. So, for example, and this is not to say they're totally bad or useless, but it's one limitation you would find in bottom-up models is that they would use like a single example of a single family home and use that archetype and say that is the single family home as we project into the future, whether it's emissions now or this year. But we saw in the previous paper that there's this big variation in designs, and we actually want a larger pool to pull from when we're estimating, kind of doing bottom-up future estimations. So that's what we did with this model. So the idea basically is that we gathered all this input data on Canada. We looked at the current state of the country, and we got this GIS data on the location of every single house and what type of house it was, every single road and the water infrastructure across the entire country. And then we split it into neighborhoods. So across Canada, you can say there's about 50,000 neighborhoods. It was based on statistical divisions. And then what we did is we quantified all of these neighborhoods. We quantified the embodied GHG and the houses and the roads and the water infrastructure, but we didn't quantify the historic emissions. We quantified it as if you had built those neighborhoods today. And then what we can do with that is now we have this data set of 50,000 neighborhoods that that we can basically resample and then build in the future as we're simulating future construction. So instead of having to rely on an archetype approach for a bottom-up model, we're able to kind of randomly sample with all these variations in the housing design, but also the neighborhood layout. Are the streets kind of in a grid fashion versus are they in like a cul-de-sac winding fashion? How is the water laid out? And then we have a great control over all that and how future construction might look. And then we can look at how that might impact future GHG emissions. So that's the main idea. There's a bit more to it. This is kind of the full figure that we have in the paper. Another thing we did was that where we didn't have, so across Canada, we didn't have full data on, say, the location of all the water infrastructure, for example. So on the data we did have, we trained a random forest model to predict what would the embodied emissions be based on neighborhood parameters, such as like how long, what's the length of certain street types you have, what kind of buildings do you have, and then we predicted the rest of the country, and that kind of filled out our data. And then again, actually what we quantified here was not just buildings. We looked at residential buildings, but we also looked at the transportation infrastructure, so the asphalt and concrete in roads. And then we also had that data that I said we extended on wastewater, stormwater use. And here we looked just at kind of local use. So we weren't looking at what if you build an entire new water treatment plant, but we looked at what if you built basically a new neighborhood with the roads you would have there. So we didn't look at like big highway infrastructure, just what we called local infrastructure that was relevant to housing. So going back and trying to answer those questions I had. So here we can extend from the building level to the overall kind of country level with looking at what's driving embodied GHG. So here, like I said, we quantified all the neighborhoods in Canada as if they were built new. So this is basically looking at potential future neighborhood designs. What impact would they have? And some of the big things we saw that were driving embodied GHG were housing. So there's about an order of magnitude difference between housing, roads, and water. So buildings have the biggest impact per person in a neighborhood. And then if you go about an order of magnitude down, so divide by 10, you have about roads. But there's some neighborhoods that have kind of a long tail on roads. So they'll have a lot of roads compared to the housing emissions. And then if you go one order of magnitude down, you have the water infrastructure. And then we found these really interesting relationships. So one of them that seems very obvious is population density. The denser you are, the lower your log emissions. But then also we found that the more single family housing you were building, so that's those detached structures that just one family lives in, the higher your embodied emissions were. But it wasn't just for the houses, it was also for the water and the road infrastructure. So we found that basically the way you build neighborhoods, if you're building like a single family neighborhood, it increases those embodied emissions across all infrastructure systems. It's not just the buildings, which is very interesting. Now I'll show you some specific examples. So again, one of the advantages of this modeling method is we build kind of individual neighborhoods and we can see the detail in them and what's driving emissions. So for example, Toronto, where I am in Canada, where I study, if we look at some of the street views of these different neighborhoods we quantified, you can see in the top left, we have these single family neighborhoods I'm talking about, which are quite high emissions per person, compared to if you have like a multi-unit neighborhood, you will have quite lower emissions. Those tend to be a bit denser. And in the bottom left, you can see you have this mid or high-rise neighborhood. And even though we have a lot higher density here, it's not necessarily better in terms of body emissions per person, because specifically in Toronto, we have a bunch of people working in finance that kind of live one person to an apartment. And these apartments would have very high, very large, say, underground parking. So you don't get as good use of your embodied emissions per person because you just have one person per apartment, whereas with these multi-unit buildings, you'll have families living in. We see a similar trend in Montreal. So those single-family neighborhoods, again, tend to have quite high emissions per person compared to a dense downtown. And then actually the city of Montreal in Canada has some of the lowest embodied emissions per person neighborhoods. And these are these, I would say, European style, low-rise multi-unit neighborhoods you see on the bottom, where each of these buildings, they're very dense. The road layouts are efficient. And then also every floor of these buildings is apartment. So each of these floors has an apartment with multiple people living in them. So very efficient use of materials. And then same thing, we see this consistent trend across the country. So this trend of single family housing increasing the embodied emissions is constant no matter the geography. So next, we use this model to do a forecast of construction emissions. So like I said, we quantify all the neighborhoods as if they're built new, and that gives us a big data set to basically rebuild neighborhoods in the future. So we just resample and simulate what future construction might look like. And then we're able to kind of turn all these knobs to see what the strategies, the best strategies are for reducing embodied emissions. So the first thing we do is we just do a baseline estimate. What if we keep building like we do now? We can see the emissions. And then we say, what if we built all that housing we need that I said at the start of the presentation? So what if we build those, it's 5.8 million homes by 2030 so that everyone has affordable housing, but we build them the way we're building now. And we can see it's this huge huge increase of emissions in the year 2030. And then this dotted line I put on the chart is what the federal reduction target is if we're just kind of proportionally downscale the sector. So by 2030, this is what we want our emissions to be at. So how low can we go with the different strategies? We look at a bunch of things that maybe we can go through in more detail at the end. We looked at change in the form of neighborhoods. We looked at design, like I said, has a big impact, improving material manufacturing on the production side, and then also some circularity strategies. So repurposing existing buildings and then not having to build new infrastructure because you've built up areas. And now I think the biggest takeaway here is that we find that changing form and then improving building design, so capturing that building design through that big data set of buildings we have the best chance of reducing embodied emissions in the future, at least in the near term. And then we see other strategies are useful as well. One thing to note here is some of the circularity strategies are not as effective in Canada, just because we are building much more new housing right now than you would be in Europe, for example. So there's not as good of, say, an urban mind, or there's just so much more new demand for materials that you can't reuse as much as you would think. So just kind of wrapping up and going over what's interesting about this method. So we get this high level of detail by quantifying all of Canada, but at the same time, we can scale up and we can do country level projections. Another thing here is we capture a lot of variability. So like I said, instead of using archetypes, we have this distribution of materials in different housing types. And we also have different designs. We have different layouts of neighborhoods, and we can kind of turn all these knobs to get a very detailed understanding of what strategies are effective. And then another thing here is this method sort of plays well with what we're seeing lately, which is there's a lot of detailed material use data on buildings coming out. So in the past, we had to use archetypes because we just didn't have the data on a bunch of the material use in a bunch of different single family homes. But we've seen in the last 5 years that through great work in the industrial ecology communities, we're getting very detailed data sets on the embodied emissions in roads, say in the entire world, like Lola did a few years ago, or building emissions. So we can use those and leverage them with these kinds of methods to have more detailed estimates of future emissions. So I think I'll wrap up there. I mentioned some of the outcomes here, where we need immediate changes in the way we design buildings and also the way we kind of design form in the urban environment to hit our emissions targets in Canada and other places as well. There's some links to the papers you can scan here, and yeah, thanks, and happy to or looking forward to the discussion.
Keagan, thank you so much, both for contributing to the database and to the modeling tool suite of our field. So this was really a lot of material to digest. Again, immediate follow-up questions before we open a general discussion later. Please raise your hand now. There's some applause. Very good. There's a lot of applause, of course. And that means let us now move on to Lola, third speaker of today, Lola Rousseau, a doctoral candidate at NTNU Trondheim, working on the material stock flow service nexus for Oslo and the Greater Norway capital region. Lola, you're sharing your screen now. Exactly.
Okay, share the slides.
And exactly now toggle the view.
Yes, is it the correct slide you're seeing?
We're seeing now the
No.
presenter's view. Exactly.
You see the presenter. How can I switch this? Let me see. Maybe swap. No.
Try to swap. Yes, there it is.
That looks good?
Yes. Perfect.
Okay, great. Thank you. So thank you for organizing and for the nice presentations from Yupeng and from Keagan. I will be scaling a bit down because we had from the global buildings, and then Keagan talked about Canada. And right now I will be looking at a specific region in Norway. Yes, so why we were interested into this region and the topic I'm going to talk about. So both the components of the built environment, we know they use large amount of materials, and we were interested to look at infrastructure and buildings because the way they might, or the way they're spatially arranged in space could have different consequences on mobility or energy use, material use, which we call like locking. So that's what we were like interested to look at, compare or like look at different built environment components and the how like they might have impacts on different aspects. So the scope of our study, we are looking at the Greater Oslo Area. You have Oslo here in the middle, and we are covering other counties all around the city. We have divided the region into 19 subregions. So we decided to focus on this extended region because the population is expected to increase, and it's covering diversity of urban, rural areas. So you have Oslo, which is quite urban, while the rest might be peri-urban or even rural. I will show you a map afterwards. And we wanted to have a comprehensive analysis of different components. So we are focusing on the residential buildings, only the residential. We are not looking at the non-residential. For the infrastructure, we look at different types of paved surfaces. So we have the roads, different types of roads, highway or private roads, municipal roads, different types of paths for pedestrians and bicycles. And we are also including roundabouts and parking. For the vehicles, or like we're looking at the mobility, we look at passenger vehicles specifically and not other types of mobility. And we wanted to, the main goal was to estimate stocks and flows of materials and the embodied GHG emissions, so related to the production of these materials over a period of until 2050. So we have these three research questions that we were interested in. First, having an understanding of what's the composition of the stock for the three components of the three sectors we're looking at for 2022. And then we have scenarios to estimate how much materials could be used towards 2050. And the last question we were interested in was to see, can we implement some resource efficiency strategies or have some decarbonization of the supply chain of the materials that could contribute to both reduce material use and the GHG emissions. Let me tell you a bit more about the region we're looking at. First, we calculated the share of the urban settlements and made the map of it. And we can see, so we have, let me find the point here. So you have Oslo right in the middle with the city center, and it's really decreasing fast. How like the share of urban settlements in each of the region is decreasing when you are looking at further away from the city center of Oslo. Then we have a similar pattern that we can observe with the population density. So we have a wide range of population density in the area. And we also looked at where the population is mostly expected to increase. Since the population is the driver of the model afterwards, it was important to see in which regions would we expect most increase. And it seems like some areas are expected, especially this one, which is not so close to the coast, is expected to increase quite a lot. We were first as well looking at different indicators related to the environment and the distance to the city center, to first have an overview of how, for example, the floor area per capita, so for residential buildings only, is changing, and what's the share of single family houses. So we observe very similar pattern that you can see in other studies, that as you get further away from the city center, you have more flora per capita, so people live maybe bigger buildings, or they have fewer people in the buildings, and the share of single family houses is also increasing. We have some sort of outliers that are, so two of the subregions of Oslo, Oslo South and Oslo West, they are still part of Oslo, but they have quite a large share of single family houses. And we have not really looked at any socio-economic indicators that might maybe explain why you would still live in Oslo, so very centrally, but you would still have a single family house. Maybe it could be related to income or other factors, but we have not looked into that. We also looked at the infrastructure, so how much square meter of paved area you would have per person, and it's exponentially increasing as you get further away. So it was a bit surprising for the region, which is quite like north of the big region we look at, but it's quite a rural places where you might not have many people living, or you actually don't have many people living, and also not so many residential buildings, but you still have the infrastructure that is there. So it was something interesting to see. And we also looked a bit at where maybe, for example, some of the cabins are located. So for Norway, it's also common to own a cabin or go on weekends or for vacation at the cabin. So you always need the infrastructure to reach these places. The third sector we were looking at, so the passenger vehicles, we were interested to see in the car ownership, so how many cars were owned per capita. And we observed some sort of a curve that is going towards the limit, which kind of makes sense because maybe comparing to infrastructure, the car is something that you own and it's like personal good. So you might not have an infinite amount of car, but it's still increasing and reaching something like 0.6 car per person, which I think compared to maybe other countries could be a bit lower, but it's still, when we see the difference between someone living in the city center and someone living further away, we still have double of the number of car per capita. And then we looked at the distance driven, so this is only this is the passenger kilometer per year per person, but only by car. And we have also this large increase as you get further away. So when you're living further away from Oslo, then you would either drive more often or drive longer distance. So all of these parameters, they were like indicating something, that there are probably some relationships between these sectors that we wanted to investigate even further and try to model to estimate the stocks and flows of materials. But first, about the stock in 2022. So we used archetypes. I know Keagan highlighted some of the limitations, but for us it was very convenient for the work we wanted to do. So for specifically this research, I developed some archetypes for the roads for Norway, but then we have Sarah, a colleague of mine, we developed archetypes for the Norwegian buildings, different typologies, different cohorts, and I was using archetypes already existing in Odin Rec for the cars. I will say a bit more about that afterwards. So we estimated the amount of materials in 2022, and a large amount of the materials are located in the infrastructure that might some surprising compared to maybe other studies, but if we look at Oslo specifically, we have, maybe I can show you a well-balanced distribution between the residential building and the infrastructure in terms of the stock. But outside Oslo, then the infrastructure materials are actually dominating compared to the residential buildings. And if we look then at the materials in terms of, so the first graph was per capita, so how much material on per capita. So in the regions that were not so populated, then of course you would have more materials per person. But then when we look at per square kilometer in Oslo, which is here in purple, then it's really high because it's quite dense in terms of built environment. And we were also interested to see at, so within Oslo, the 4 different neighborhoods or boroughs, how they differentiate. And while for the very center, most of the materials are located in the residential buildings and some is located in the infrastructure, directly for the other boroughs, then it gets kind of equal and the infrastructure is actually taking a larger share. For modeling the stocks and the flows, the future stocks and flows, we use the resource efficiency and climate change model developed by Stefan. It was very convenient as it's available open source on GitHub, and it has been it's well documented because it has been used in this resource efficiency and climate change report, and there's a lot of papers that have used the ODIMREC model. And Stefan has made a very nice page collecting everything related to the documentation, the databases. So it's actually quite nice to build upon the model. And that's what we did. So we used the ODIMREC to build an integrated residential buildings infrastructure car fleet model. And the model starts using different parameters, the population, so the future scenario for the population. So we had for each of the subregions. And then we made scenarios on the floor area per capita, a business as usual scenario where we would continue the growth, the historic growth in floor area per capita, or a sufficiency scenario where we would decrease the floor area per capita. And we also had scenarios on the type split, so the type split of the new buildings. For the business as usual, we kept a constant share of new buildings, while in the sufficiency, we were thinking maybe we can ban new single-family houses and see what happens. So based on the parameters related to the building and the growth of population, we could calculate the stock of the future residential buildings until 2050. We had some regression analysis to be able to estimate some relationships between the residential buildings and the infrastructure. And we thought, or like we assumed, that it would be kept constant as we observed the patterns that we observed today, that we could keep that constant in the future, and this would allow us to evaluate how much infrastructure is needed. And then based on similar analysis, using regression analysis with the residential buildings and the infrastructure, then we estimated how the per capita passenger kilometer would be changing. So again, assuming similar pattern as today's would apply in the future. And having additional parameters related to the vehicles, one of the parameters, so most of the parameters are not changing here, and it's only the type split that would be changing. We are assuming that we continue the historical growth in electric vehicles in Norway, so Norway is one of the countries with a very large share of electric vehicles. So we assume we are actually reaching 100% of new vehicles in the future, so following the trend. And this would allow us to estimate the stock of cars. Using the parameters of the system, like material intensities or energy intensities, everything related to enable us to calculate the materials. And we had 2 scenarios on the material production. So the first one is baseline scenario, so no mitigation. And the second one, which is available in ODIMREC, which is the decarbonization scenario, where you decarbonize the electricity and you introduce some technological changes, such as a better efficiency in the aluminum production or introduction of hydrogen in the iron and steel production. And thanks to all of that, we were able to get what we wanted to estimate, which is the material stocks and flows and the embodied GHG emissions. So we were we use the ODIMREC software that we have slightly modified to connect the sectors together. And right now, and we were able to answer the following question, like how would the stock look like in 2050? And not so much different compared to actually today. This is for the residential buildings, where we could first see that, yes, there is a larger share of the materials that are located in apartment blocks, and a large share as well in single-family house, so not so many multi-family houses. And in our business as usual scenario, this would be gently growing. And if we introduce the sufficiency scenario, so actually reducing flora per capita, we might only manage to keep a constant stock until 2050. And the large share of the materials are from aggregate and cement, which is used in concrete. And there's also a large use of wood already in Norway, especially in single-family houses and multi-family houses. Regarding the infrastructure, we don't see a lot of changes, a lot of aggregates needed. Yes, so we are not, the way that we have modeled the scenario or the connection between the sectors in not introducing a lot of changes in the amount of infrastructure that might be needed. And regarding the cars, since we have introduced the continuation of adoption of electric vehicles, we see that we would potentially reach 100% electric vehicles in 2050, and this would have some consequences in the stock of the materials, a larger share of copper and zinc, for example. But in terms of the total stock of the materials needed in the cars, this is only slightly reducing or staying constant in our business as usual scenario. And we were also interested to look at the car ownership, if there were any changes that could be introduced by changing what we did with the residential buildings. So for 2022, there was on average 0.47 cars per capita across the entire region. But then with the scenarios, we see that even with the sufficiency, we would only slightly reduce the cars. So what we can think of is that just changing some aspects in the built environment will not have a lot of effects on the mobility itself, because buildings have a long lifetime. So we are not able to drastically change the way things have been built. So there is a need for extra incentives to encourage to switch from cars to other mobility aspects. So even if we would maybe reduce per capita the number of cars in terms of the total number of cars in the stock, we see that we would still be increasing because the population is increasing. So this is not compensating, the reduction in car per capita is not compensating the growth of population. Regarding the flows of the materials until 2050, since I was showing you the stock, we were also able to just to make a graph with the materials that were needed, and we see that there is a large share of aggregates that is needed for the roads, the infrastructures, so for maintaining them or building the new ones, and also a large share of aggregates and with the cement for the apartment blocks, and then the wood for single-family houses and multi-family houses. All the other materials that are in the gray are not directly shown because it's a lot of other materials for the cars, for example, but the quantities are very small, so we wouldn't have been able to see anything on the map or the graph. But then when we look at the GHG emissions, then suddenly, for example, steel and iron, that is very tiny quantity compared to the aggregate, they are requiring or like have much more emissions. And same with cement, that was for here for apartment blocks, and we might need this also a bit for some of the other residential buildings. They have high embodied emissions. And if we look at what the potential of our scenario compared to the business as usual, in terms of final consumption of materials, we would potentially be able to reduce by almost a third the final consumption of materials. And regarding the total emissions, so it's the cumulative emissions until 2050. In going from the baseline scenario until the sufficiency scenario, we would reduce by 20%. And if we go from business as usual scenario, where we only decarbonize the materials, then we would reduce maybe by 15%. And if we combine our two scenarios, both on the residential buildings, so going from business as usual to sufficiency, plus the decarbonization of the materials, we could potentially reduce by a third the emissions related to the materials. I will go to some of the conclusions of our work. As I mentioned, the changes in the built environment were quite slow, and that means that we are not able to introduce changes related to the mobility. But it could also be that it's also difficult to model the link with mobility, and we're not looking at any other strategies such as car sharing or any social economic indicators that would encourage to switch from car to public transport, for example. And we would recommend both a combination of local actions, such as the reduction of the flora per capita, combined with some more global actions related to the supply chain of the materials for an effective mitigation. And what comes next related to this work, I was only showing the emissions related to the material production. So this is the pink share on this donut graph. And then we can see that for 2023, the use phase of the building or the use phase of the vehicles, they make more than 75% of the emissions. So it's actually quite important to also consider the use phase. We didn't want to look at it because we were not renovating the building. So that's the next step or something that is coming next. And so since we were not renovating the building, we didn't want to show a wrong image of how much energy could potentially be used in the building in the future. And yes, thank you for attending.
Lola, thank you so much for this great overview, and also good to see that your work has advanced very far, that it's currently already under peer review, right?
Yeah.
So thank you so much to all our three presenters.